So this week we're going to be talking about constraints and indexes. And it's crazy. It's week 12 already. We really only have like one more week after this one. Um, and so really, in my mind, this week and the next week are both fairly light weeks. This week we're going to kind of go over indexes and constraint, next week views. So I feel like they're a little bit lighter. And so real quick housekeeping item, if you're working on a final project, would highly recommend you use kind of these weeks and get those submitted as early as possible. Because one, you can be done with it. And for two, hopefully it frees up some room for some of your other classes. It's kind of my hope. So yeah, because these weeks are a little lighter. So anyways, what I like to do, and I know my screen is shared. We're going to use it here and there, but really I like to spend a lot of time kind of talking through indexes, because the reason why they're towards the end of the semester is because constraints are a little bit more fundamental, but indexes are something that you don't really need them until you do, but they can be game changers once you need them. But they're kind of a little bit of black magic, but I try to dumb them down in a way that kind of helps us kind of understand, because all these systems are proprietary, or programmed by people who admittedly are a lot smarter than myself. So I don't really dive into how they work at like the very technical level, but I really like to kind of break them down as far as how I think through them logically. Because I think it just helps you kind of come to grips with how we use them, that when we use them, and why. Um, so anyways, we'll start with constraints, because I feel like, well, actually, let's start with indexes. So an index, if you guys remember, in fact, let me try to find a picture. I don't know ages of those you who are here, or those who you who will watch later. But back in the old days, in fact, I kind of barely remember this. But back in the day, there were, like, in libraries and stuff, you had these like little, index card cabinets, and that's, index. That's why they're called index cards. We're going on like this little trip through history here. But I remember, like, you'd go into the library and you'd see like a little cabinet that looked something like this, that was kind of sitting there, maybe a couple of them. And they had little cards in them. And I was too young to ever like use them, but now that I kind of understand what they are, um I understand how they work. So and computers have changed this to where I feel like this is actually a harder concept for us to understand if we never had to go through this manual process, versus someone, if you had, this concept may come very easily. But now with computers, if we walk into a library, we can, if we do, but we can search for anything. Like even nowadays, like walking into Barnes and Noble, if you're looking for something in particular, it's actually somewhat difficult to find, in my experience, because you have to know like which category it's in. And like I'm a huge Brandon Sanderson fan, and so like it always throws me for a loop, because is it in teen fantasy or is it just in fantasy, yada yada. But as we know, with all things data, or like in books or anything, there are a million different ways that we could categorize things, and store things and sort things. And just like our database, libraries are storing books, and there's tons of different ways that we can organize them. And the way that we choose to store them physically on the shelves is determined on, oh, what's going to make it easiest for people to find. And so, like, I remember, back in my elementary library, they actually had them sorted, on like a combination where they had it by grade level, and then by nonfiction and fiction, and then I can't remember thereafter. But but anyways, like as an example, you can kind of see what it's like. But nowadays we can do things that are crazy. Like, hey, I want to find books that are about medieval times, and I want them to be nonfiction. Um, like we can Google that and find that information, or systems are already built to search for those keywords. But back in the old days, like we didn't have any of that. Everything was manual. And so we had these shelves just like this. And so just to put it in a very basic sense, let's say that we had our books organized by like what I mentioned back in my library, where it's organized by grade level and fiction, nonfiction, and all that. Because like let's say you're looking for a specific author or a specific book title. You're looking for a specific book title because, again, remember, we don't have the internet. Your teacher said, hey, we have this very specific book title. Can you go and get this book from the library? um and so you'd walk into the library and not knowing if the library is organized by grade level and an author. Without that information, you had no idea where it was, other than manually going shelf by shelf and looking. Which, I mean, again, think about this in a database concept. Even though databases are faster, we're talking about the same concepts, because at bulk it becomes this an expense. So you can imagine how tedious that would be, going book by book and looking manually for the name, right? And for a database without indexes, that's literally what it does. Like if you were to Google Sakila and look for a specific customer, it would literally read every row into memory and look at each one to do a comparison. It's like that book, Are You My Mother? Are you my mother? Nope. Okay. Are you my mother? Nope. Okay. So do that for every row. And so, in our customer database for 100 in a computer, it'll do it instantly, like hardly any lag. We don't even have to know that it happened, basically, which has spoiled us. But like when you become massive, like let's say like a Google, or these people that are storing just insane vast amounts of data, it can become very problematic. You have lots of users querying lots of data all the time, simultaneously. And so we want to look for ways to speed it up, because we don't want the database to search one by one. And so anyways, back to our library scenario, the librarian would have something set up like this, and maybe they would have all the books, each one of these drawers is a letter of the alphabet, or maybe a couple letters of the alphabet, or whatever. And it was filled with index cards that would have, each index card would be a book, and you could kind of flip through those, and it would say what shelf it's on, and so, or in other information. So maybe you find the card and it says what grade level, fiction, nonfiction, and what shelf. That pinpoints you directly to it. But and so then instead of browsing the whole library one by one, you can just look at the one shelf and then say, okay, there's 20 books on this shelf. Then you scan for the name and bam, you find it, right? Which is a lot easier than browsing all 100,000. So that's kind of the way the index works, is because we know, hey, the title of this book starts with this. So we go to that cabinet, and that cabinet is what we consider the metadata. It's the data about the data. And so it with just a little bit of metadata, it made the query, or going to find that book, probably at least 100 times quicker, because we know instead of looking at 100,000, we can look at 20, which is insanely fast, just by knowing what kind of letter the alphabet started with. So anyways, indexes in the database work the exact same. So when we place a constraint on, or an index on a column, it functions exactly the same. Now the difference is it kind of does it somewhat automatically. There's a couple different types of constraint of indexes that we can we can put on things. But for the most part, if we just put an index on something, it will kind of handle it for us. So for example, if I were to select everything from customer, let's run that. So we can see email here, right? That might be, so we want to put indexes on things that are common, commonly searched. Now, so let's just go over an example of how we would put an index on, like, let's say last name. So we would say create index, and then we give it a name. And I usually do the table name. So customer IDX1 on customer last name. So we say create index, we give the index a name, and we say on table, and then in parentheses, the name of the column. And it looks like I may have done this before because I got a duplicate index. But anyways, that's how we create the index. And so now if we were to do an index, search by someone's last name, it's going to be faster. And what the computer does, or what the database does, is it says, okay, I've indexed last name. So it creates this metadata. It creates its own little index cabinet. And it says, okay, the rows 1 through 50 are all start with the letter A. Rows 50 through this are B, and so on and so forth. And so again, when we say, hey, I want to find Elizabeth Brown, it says, oh, instead of looking through all 100,000 rows, I'm just going to look for rows this to this because that's where the B's are. And it might be even narrowed down. There's a couple different types of indexes, which in the reading are pretty self-explanatory depending on the type of data. So for like last name, where there's many possibilities, but can be organized by alphabet, a B tree index is may work better. There's another type of index that works better with like categorical data. So like yes, no, or like if you're on an e-commerce store and you sell men, women, and youth and teen kind of like clothing lines, like that category may be a good use of an index that suits categorical data. So anyways, there's a couple different types of options that you can take depending on the type of data. But just by throwing this index on, that's kind of how it's going to do it. It's going to kind of take and make it so it's just faster. Now, the key with building these indexes is just like when we do it in the library. Back to our library scenario, we talked about having the title of the book alphabetical, but I'm a big Brandon Sanderson fan. So let's say I want to find every Brandon Sanderson book in the library. Well, okay, let's do another index that has all of the author names alphabetical by last name. So that way I could go up, find the S drawer, pull it open, and find the little clump of Brandon Sanderson indexes that have all of his books, take them out, and then I could find them all. But the problem is, just like in the real world, I guess like the physical world, every time we add like a way to kind of search through these, every time we create that new index, all of a sudden we have this metadata. Now instead of just having one index card per book, in the one filing cabinet, now we have two, because we have to have one in the index by book title and one in the index by author. So, that comes with some overhead. And just like in the physical world, in the computer world, every time we define an index, it also has to create metadata, and it comes in the expense of overhead disk space. And there also becomes a point where if you have so many indexes, that it actually cripples your query instead of even helping it, because it also has to go into the index and find it. So you can imagine if you index everything, it's the same as if you just browsed every book, because the computer has to choose which index to use. And you can imagine how overwhelming that would be if you walked in, you know, and you had certain criteria. Because let's say you weren't just looking for one book, but let's say you were looking for 5 different books, all based on the author, the fiction, and the grade level. Like some various different things, and it could be any possible combination of those. You can imagine how trying to like compile that data would become like confusing and hard. And so there's a line, and it's not a clear line. That's like, I can't say, oh, draw the line here, because it varies. So that's why indexes are usually something that you start with, like the bare necessities, and then there's a whole realm of like work out there for SQL tuning, is what it's called. And SQL tuning is simply just a matter of, let me look at the queries that are ran most. What's holding them up? What's the bottleneck? Can we fix it just in the query? If not, can we add an index to make this faster? So anyways, needless to say, they come with some overhead. So you don't want to just index everything. You just want to index those common variables, because the computer's already pretty fast. It's just those commonly used things that can make a big difference and still kind of keep you running lean. So anyways, is that making sense so far? You guys
Yep.
both said you remember the index card, so you're very well versed.
Yep. We get it.
Yeah. So anyways, what's cool, I always like to kind of bring it back to the real world, because it helps to make sense, because ultimately the people who have built these algorithms and these constructs, essentially they based it on real world problems, because ultimately they're the same. So I like to kind of tone it back, take the complexity out of it, think about it in a real level. And so hopefully that helped a little. So now to get into constraints, because they kind of go a little hand in hand, because sometimes you can create them together. So oftentimes, like, and you guys have probably already seen some example of constraint if you've built your ERD, or if you remember back to when we were talking about ERDs. We could mark columns as being not null, meaning they can't be empty. That's one example of a constraint. So we can add a not null constraint to any column to say, hey, it can't be empty. There's a check constraint to say, like, oh, this column has to be male or female, or yes or no, and those kinds of things. So there's a couple of those that you'll see in the reading. But one of the ones that I like to talk about that's a little bit more, because those ones are all fairly self-explanatory. But the one that I like to highlight is when you create a certain index, you can create what's called a unique index. So just like when we created our first index, we can say create a unique index. And basically what this means is it's not only going to index it, but it's going to put a constraint on it as well, meaning that every value in there has to be unique. So for example, email, we don't want 2 customers with the same email, because 1, that's a security risk, and 2, it just should never happen. So what we do is we place a unique index on email, because we're also searching for email constantly. So we place a unique index on customer email. And what that does is it means that now it's going to search for those faster, because it's created an index for them, but it also won't allow multiple emails. Now, an example of this is, because the difference is when we build these indexes, back to our book thing, right? What if there's 2 books that have the same title? If we go back to our book scenario. Now, if those 2 books have the same title, we have to continually search through that whole, like, even though we kind of nailed down into that specific index, like, okay, here's the B cabinet, we flip through all those cards. And if we know that there's a possibility there being 2 books with the same title, we need to find both of those. So once we draw card 1, we still have to continually search till we find card 2. or, or until we hit the end. And then we know, okay, we exhausted it. There was only one. And so unique index is helpful because in the case of like an email, and we know, hey, there's a business purpose that there can only be one, right? The minute we pull that first card or the minute the database identifies that row, it can stop looking. So if we say, hey, select everything from customer where the email is equal to this, it knows, hey, there's a unique index on this email column. The minute I find what I'm looking for, I'm done. I don't need to continually search. I can be done. So the unique index is unique and helpful because basically if there's only one of something, you can place the unique index on there, and as soon as it finds it, it stops looking, which can also save more time in addition to the plain old index, if it makes sense, because obviously you wouldn't want to put a unique index on last name because multiple people might share the same last name. Does that make sense?
Yep.
Awesome. Cool. Well, I'm going to try and keep this one a little short, because like I said, it's kind of lighter week. And my voice is kind of going out on me a little bit, but do you guys have any questions or anything like that? The exercises this week are fairly straightforward. I kind of poked through them. I didn't really see a need to necessarily go over them like we have done in the past. But do you have any questions about that or final or anything like that?
I think I'm okay.
Yep. I think that's it.
Alrighty. Well, perfect. Well, we'll keep this to a minimum. And if you guys have any questions along the way, feel free to reach out. Otherwise, have a great week.
Thank you. You too.
Yep. Thank
Thanks.
you.